Welcome to the Deep Dive. We're here to unpack complex research and make it, usable knowledge for you. Today we're looking at LongLive. It's a really interesting new framework for generating long videos, interactively in real time. Think about creating high-quality video that stretches on, but also video that you can actually steer as it's being made. Our goal here is pretty clear. Get under the hood of LongLive. We want to understand the core ideas that make this possible. There are essentially three key innovations we need to break down KV-recache, streaming long tuning, and this combination of frame sync and short window attention. These tackle the big problems: speed, keeping quality over time, and that real-time control. So let's get into it. What was the fundamental problem they were facing first?
Well, it really boils down to this dual challenge in video generation. You need fantastic visual quality, right? But you also need it to be generated efficiently. And historically, models have really struggled to deliver both. There's usually a trade-off. Take diffusion models or diffusion-forcing models. They're known for really high-quality output. The visuals are often stunning, but the downside is speed. They are incredibly slow, especially when you try to make longer videos.
Why is that? What's the technical reason?
It comes down to how they process information. They tend to use bidirectional attention. That means the model looks forwards and backwards across the whole sequence at once. And because of that, you can't use something called key value caching.
Okay, and KV caching is important because
It's a huge speed-up technique. It lets the model reuse calculations from previous steps, so it doesn't have to recompute everything constantly. Without it, inference is just way too slow for anything real-time. Think about a model like Skyreel's V2. The paper mentions it takes around 50 minutes on a powerful H100 GPU just to make a 60-second clip.
Wow, okay. 50 minutes for 1 minute. That puts the challenge into perspective. Real-time interaction is completely off the table there.
Exactly. So then you have the other side. Models using causal attention, specifically autoregressive or AR models. These can use KV caching, so in theory, they should be much faster.
But they have their own problems.
They do. The big one is quality degradation, especially over longer durations. Things start to drift, the video loses consistency. This often happens because of how they're trained, the train short test long issue. They learn on short clips, but then during inference, they have to generate much longer sequences. Small errors that creep in just build up and accumulate over time.
Right, so LongLive needed a different approach. They went with a causal, frame-level AR design, trying to get the speed benefits, but solve those consistency issues.
Precisely. They engineered it from the ground up for efficiency and interaction.
Okay, let's talk about that interaction piece. Being able to change the prompt midstream. That sounds tricky. How do you avoid just, a jarring cut?
That's a core difficulty. When you feed in a new prompt, the model has a dilemma. Option 1, throw away all the past context, the KV cache. If you do that, the model will follow the new prompt really well, but visually. It's abrupt, you get a hard cut, a loss of temporal smoothness.
Not ideal for a continuous narrative.
Not at all. Option 2, keep the whole KV cache to maintain that smooth visual flow. The problem there is the model often gets stuck on the old prompt. The cache is full of information or residual semantics from the previous instruction.
Prompt inertia, they call it.
That's the term, yeah. Prompt inertia. The model lags or even ignores the new prompt because it's still influenced too heavily by the past.
So it's either a jarring visual jump or the story doesn't change when you want it to. How does LongLive solution KV-recache fix this?
KV-recache is quite elegant, really. It finds a middle path. When a prompt changes, it doesn't just discard or keep the entire cache, it refreshes it. It uses the frames that have already been generated to maintain the visual continuity, the motion, the scene details, but it combines that visual information with the new prompt to recompute the key value states.
I see. So it keeps the visual history, but updates the semantic meaning based on the new instruction.
Exactly. It effectively fleshes out the old comp's semantic residue while holding on to the necessary visual context.
And the result shown in the paper, based on their figure 3, is a smooth transition that fully respects the new prompt. That seems like a key breakthrough for usability.
Definitely. It tackles that core interactive challenge directly.
Okay, interaction solved. Let's go back to the length issue. Even with KV-recache, how do they prevent that quality drift we talked about with AR models, the train short test long problem, causing errors to build up?
Right. That required a change in the training strategy itself. This is where streaming long tuning comes into play. The core idea is to align the training process much more closely with how inference actually works for long videos, so a train long, test long approach.
How do they train long without running into memory limits? Training on minute-long sequences must be computationally expensive.
It would be, yes. Trying to backpropagate through a very long sequence would likely cause out-of-memory, or OM, errors. So they use a streaming method. During training, the model generates the video in shorter chunks, say 5 seconds at a time. Crucially, each new chunk is generated conditioned on the KV-recache from the previous chunk that the model itself generated, including any imperfections or small errors.
So it learns to handle its own mistakes, essentially.
In a way, yes. It's exposed to the kind of cascading effects that happen during long inference, making it more robust. And for efficiency, the gradients of the learning signals are only calculated for the most recent chunk being generated.
I see. So the memory needed stays roughly constant, tied to the chunk size, not the total video length.
That's the key. It avoids the memory explosion. And it works. They mentioned fine-tuning a 1.3 billion parameter model for minute-long generation using just 32 GPU days. That's quite efficient for this scale.
That efficiency is impressive. And this streaming long tuning makes the model tough enough for the next step, which is about inference speed.
Right. It lays the foundation for the high-speed inference techniques. Because the model is already robust to long sequences, they can apply attention mechanisms that are much faster but might otherwise hurt quality.
Okay, let's get into those. How did they achieve real-time speed while still keeping things consistent over, say, several minutes?
The main technique here is short window attention.
Instead of looking at the whole sequence.
Exactly. Standard attention looks back at everything, and the computation cost grows, well, quadratically with the length. It gets very expensive very fast. Short window attention restricts the model to only look at a small, fixed-size window of recent frames, maybe the last 16 or so.
That obviously cuts down computation and memory hugely.
Dramatically. The cost becomes proportional to the window size, which is constant, not the growing video length.
But doesn't that create the opposite problem? If it only looks back a few seconds, how does it remember what happened at the beginning of the video? Doesn't it lose long-range consistency?
It absolutely would. That's the inherent trade-off with purely local attention.
Okay.
You gain speed, but you lose that global context.
So how did they fix that?
This is where the frame sync comes in. It's a really clever addition. They designate the very first chunk of frames in the video as special sync tokens. Think of them as permanent anchors.
Anchors. How do they work?
These initial frame tokens are kept in the KV-recache permanently, and critically, they are added or concatenated to the keys and values in every attention block, even as the short attention window slides forward.
So even when the model is calculating attention based on recent frames, it also always gets to look back at those initial anchor frames.
Precisely. Those first frames become globally accessible throughout the entire generation process, providing a constant reference point.
That bridges the gap then. Short window gives the speed, frame sync brings back the long-range memory.
Yes, it mitigates that quality loss from the short window. It lets them have both efficiency and consistency.
And did this combination yield measurable gains?
Oh, yes. The paper states this pairing reduced the overall compute time by 28% and cut peak memory use by 17% on an H100. Significant savings.
Okay, let's talk bottom line performance. Just how fast is LongLive? And how long can it realistically generate video for?
The numbers are quite striking. For inference speed, it hits 20.7 frames per second on a single NVIDIA H100 GPU.
That's definitely real time.
It is. And they compare it to Skyreel's V2, reporting that LongLive is over 41 times faster.
41 times faster. That's a huge leap. And the maximum length.
They demonstrate stable generation up to 240 seconds. That's 4 minutes on that single H100, maintaining quality.
4 minutes at real-time speeds. Impressive. Did they have to sacrifice visual quality significantly to achieve this, according to benchmarks?
Not according to the VBench scores they report. They achieved strong scores, like 84.87 for short videos, and importantly, it stayed high at 84.38 even for the interactive long video setting. That suggests the streaming long tuning and frame sync are really working to prevent drift. They also explored quantization using lower precision numbers, INT8, to make the model smaller and potentially faster.
Did that work out?
It did. It shrunk the model size roughly in half from 2.7 gigalia to 1.4 gilias and actually boosted throughput slightly from about 12.6 FPS to 16.4 FPS, with apparently only a minor hit to quality.
So faster, longer, still high quality. What did actual users think when comparing it?
The user study results seem to back it up. When compared against same Skyreels V2, users preferred LongLive significantly. For visual quality, it was about 49% preference for LongLive versus 18% for the competitor, and maybe even more telling for the interactive aspect. On instruction following, LongLive got nearly 48% preference compared to about 26%.
That suggests users felt it was both better looking and actually did what they asked it to do when changing prompts.
It really points to the successful integration of all those pieces we discussed. The KV-recache for smooth interaction, the streaming long tuning for robustness, and that frame sync short window combo for efficient, consistent long generation.
It really feels like a complete system when you step back and think about fine-tuning a large 1.3 billion parameter model to generate reliably for 4 minutes, and doing it by making the training process mirror that long inference. That's quite an engineering achievement.
It is. It required tackling multiple bottlenecks simultaneously.
Yeah, it wasn't just one trick. It was how KV-recache solved the interaction inertia, how streaming long tuning fixed the train test mismatch, and how the frame sync counteracted the downside of short window attention. They built solutions that directly addressed the problems created by other necessary components. It feels like they've genuinely moved the needle on making this kind of user-guided, long-form video generation practical, not just theoretical. A really solid piece of work.